On November 7, 1940, the Tacoma Narrows Bridge in Washington state, nicknamed Galloping Gertie, collapsed in moderate winds after just 4 months of operation. Remarkably, only one life was lost, a dog trapped in a car, but the collapse became one of the most famous engineering failures in history, captured on film and shown in physics and engineering classes ever since. The bridge, completed in July 1940, was a stunning suspension bridge spanning the Tacoma Narrows Strait. At 2,800 feet, it was the third longest suspension bridge in the world and an engineering marvel, sleek, modern, beautiful. But from opening day, the bridge had an alarming problem. It moved. Even in gentle winds, the roadway would undulate in waves, rising and falling several feet. Drivers reported feeling seasick crossing it. Engineers noticed but weren't overly concerned initially. Suspension bridges were expected to move somewhat. The bridge became a tourist attraction. People came to experience the thrilling ride across Galloping Gertie. On the morning of November 7th, winds of about 40 miles per hour hit the bridge, not hurricane force, just moderate winds, but something different happened. Instead of the familiar up and down rolling motion, the bridge began twisting violently, one side lifting while the other dropped, the roadway corkscrewing along its length. This torsional motion grew more extreme. The bridge was tearing itself apart. At 11 a.m., after hours of violent twisting, the center span broke apart and crashed into Puget Sound below. The only fatality was Tubby, a black cocker spaniel trapped in a car abandoned on the bridge, too terrified to be rescued. The collapse was filmed by Barney Elliott, a local camera shop owner and the Tacoma News-Tribune photographer, creating footage that would be studied for decades. This is the story of Galloping Gertie, the bridge that danced itself to death. Part 1. Building Galloping Gertie. The need. 1930s Washington state. Tacoma and the Olympic Peninsula separated by Puget Sound. The Tacoma Narrows Strait, about 1 mile wide. Ferry service existed but was slow and limited. Growing automobile traffic demanded a bridge. The design. Engineer Leon Moiseeff designed the Tacoma Narrows Bridge. Suspension bridge design. Main span 2,800 feet, 853 meters. Total length 5,939 feet, including approaches. 2 towers 425 feet high. Roadway suspended from cables. Sleek, modern, elegant design. Very narrow deck, 39 feet wide. Very shallow stiffening girders, 8 feet deep. This slender design was aesthetically beautiful but structurally problematic. The philosophy, deflection theory. Moiseeff believed lighter, more flexible bridges were modern and efficient, used less material, cheaper, could handle loads through flexibility. His deflection theory suggested this was safe, but this theory had fatal flaws. Construction. Built in 1938 to 1940. Cost $6.4 million. Open to traffic July 1, 1940. Celebrated as engineering triumph, graceful, economical design. The third longest suspension bridge in the world. Opening day, crowds celebrated. The bridge was beautiful, but from day one, it moved. Part 2. The galloping begins. The problem appears immediately. Opening day, July 1st, 1940. Even in gentle winds, the bridge roadway undulated, rising and falling in waves. Drivers felt like they were on ocean swells. Some drivers experienced motion sickness. Alarming, but initially dismissed as minor. The nickname. Workers during construction called it Galloping Gertie. The public adopted the name. The bridge galloped like a horse. sometimes movements of 4 to 5 feet up and down. The attraction. Rather than avoid it, people sought it out. Thrill seekers came to experience the ride. Photographers captured the undulations. Became a tourist attraction. Come ride Galloping Gertie. People thought it was exciting, not dangerous. The engineers' response. Concerns were raised. Engineers studied the oscillations. Various theories proposed. Some measures attempted, like tie-down cables and hydraulic dampers, but nothing stopped the movement. Moisseiff insisted it was within acceptable limits. Fundamentally, they didn't fully understand what was happening. The witnesses. Regular users reported seeing cars ahead disappear from view as the roadway dipped, feeling like being on a roller coaster. White-knuckled crossing experiences. Some refused to drive across. Others loved the thrill. But for 4 months, the bridge stood, undulating but surviving. November 7th, 1940, would be different. Part 3, November 7th, 1940, the final dance. The morning. 7 a.m., wind picks up. Moderate winds of about 35 to 40 miles per hour, not unusually strong for the area. But the bridge's response was different. Instead of the familiar vertical galloping motion, the bridge began twisting. Torsional oscillation. One side of roadway lifting while the other dropped. The entire span corkscrewing. Far more violent than previous movements. 8:30 a.m., traffic stopped. Bridge authorities closed the bridge to traffic. Too dangerous to cross. A few cars already on the bridge. Leonard Coatsworth, the last driver. A man and his dog. Leonard Coatsworth, a Tacoma News Tribune editor, driving his car with his daughter's cocker spaniel Tubby in the back. Got onto the bridge just before closure. Found himself on a wildly bucking, twisting roadway. His experience. The roadway tilting 45 degrees side to side. His car sliding across the deck. He abandoned the car and crawled on hands and knees toward the tower. Reached safety. But Tubby was too terrified to leave the car. The dog bit Coatsworth when he tried to rescue him. Coatsworth had to leave Tubby behind. 8 to 11 a.m., the death dance. For hours, the bridge twisted violently. Engineers, officials, and spectators watched. Barney Elliott set up his camera, filmed the destruction. The bridge writhing like a living thing, twisting, bucking, corkscrewing. The forces involved. Aerodynamic flutter. Resonance amplifying movement. Structural stress mounting. Materials fatiguing. Each oscillation weakened the structure more. Part 4, 11 a.m., the collapse. The breaking point. 10:30 a.m., structural failure beginning. Suspender cables snapping, concrete cracking, steel buckling, center span breaking apart. 11 a.m., center span falls. The center section of the bridge broke free. 600 feet of roadway. Crashed into Puget Sound 190 feet below. Massive splash. Steel and concrete disappearing into the water. Then more sections followed. Additional portions of the suspended roadway, piece by piece falling. The towers remained standing, but the roadway was gone. By 11:10 a.m., the center 2,800-foot span was destroyed. Only the towers and cables remained, twisted wreckage in the water below. The lone casualty? Tubby, the Cocker Spaniel, still in Coatsworth's abandoned car, went down with the bridge section, the only death. The footage. Barney Elliott's film captured everything: the violent twisting, the graceful bridge becoming a death dance, the dramatic collapse. Became one of the most famous pieces of engineering failure footage, shown in physics and engineering classes worldwide, studied for decades. The film made the Tacoma Narrows collapse legendary. Part 5. The investigation. Why did it fail? The questions. Engineers worldwide asked, how did a modern bridge collapse in moderate winds? What went wrong? How to prevent in future? The investigation. Federal and state authorities studied the failure. Initial theories: resonance, wind frequency matching the bridge's natural frequency; aerodynamic instability, insufficient stiffness, poor design. The real cause: aeroelastic flutter. What actually happened? The bridge's slender, flexible design created aerodynamic instability. Wind flowing over and under the roadway created vortices, whirlpools of air. These vortices caused pressure differences, which induced torsional oscillation. This oscillation fed back into the airflow, creating a self-reinforcing cycle, amplifying movement until structural failure. This phenomenon is called aeroelastic flutter. The design flaws. Specific problems. 1. Too slender. The roadway was too narrow and shallow, inadequate stiffness to resist torsion. Modern suspension bridges need adequate depth. 2. Solid girders. The shallow solid plate girders acted like sails, caught wind rather than letting it pass through. Modern designs use open trusses. 3. Deflection theory was wrong. Moiseieff's theory didn't account for aerodynamic forces. Flexibility was dangerous, not safe. Revolutionized bridge engineering understanding. The lessons. What engineers learned. 1. Aerodynamics matter. Bridge designs must consider wind forces carefully, not just static loads, dynamic, oscillating forces. 2. Stiffness required. Suspension bridges need adequate stiffness, deep trusses, not shallow girders. Width to span ratios matter. 3. Wind tunnel testing. Models must be tested in wind tunnels before construction, mandatory for modern bridges. 4. Dampening systems. Modern bridges include systems to dampen oscillations, prevent resonance buildup. These lessons transformed bridge engineering worldwide. Part 6. The legacy and rebuild. The immediate impact. The collapse was a sensation. Newsreels showed footage worldwide. Engineering schools studied it, became textbook example of failure. Bridge design philosophy changed. The investigation results. The official report concluded, design was fundamentally flawed. Aerodynamic instability the cause. Moiseieff's deflection theory discredited. New standards needed. The replacement. A new Tacoma Narrows Bridge was needed. Designed with lessons learned. Construction began 1948, opened October 14, 1950. Much stiffer design. Open truss instead of solid girders. Wider roadway. Adequate depth for stiffness. Wind tunnel tested. This bridge still stands today, stable and safe. The original wreckage. The collapsed sections remain on the bottom of Puget Sound, now an artificial reef, popular dive site. Marine life has colonized the wreckage, designated underwater heritage site. The film, Barney Elliott's footage, became legendary, studied by generations of engineers, shown in physics classes, often incorrectly explained as simple resonance, available online. One of the most educational disaster films ever made. Modern understanding. Engineers now know the collapse wasn't simple resonance. It was complex aeroelastic flutter, multiple forces interacting, a phenomenon now well understood and prevented in modern designs. The Tacoma Narrows collapse advanced bridge engineering by decades. Conclusion. On November 7, 1940, the Tacoma Narrows Bridge, Galloping Gertie, collapsed after 4 months of operation. From opening day, the bridge had undulated in wind, earning its nickname. Engineers noticed but didn't fully understand the danger. People came to experience the thrilling ride. On November 7th, moderate 40-mile-per-hour winds caused something different, violent twisting, not just vertical movement. For hours, the bridge corkscrewed. At 11 a.m., it broke apart and fell into Puget Sound. Remarkably, only one life was lost, Tubby, a Cocker Spaniel trapped in an abandoned car. But the collapse revolutionized bridge engineering. The bridge failed because the design was too slender and flexible. Aerodynamic forces created self-reinforcing oscillations. Aeroelastic flutter tore the bridge apart. Engineers didn't fully understand wind forces on flexible structures. The lessons learned: modern bridges are stiffer, aerodynamics are carefully considered, wind tunnel testing is mandatory. The Tacoma Narrows collapse changed engineering forever. Rest in peace to Tubby, the Cocker Spaniel, the only victim of Galloping Gertie. November 7, 1940, the day a bridge danced itself to death. A tragic failure, but a lesson that saved countless lives by transforming bridge design. Galloping Gertie, gone but never forgotten. Her collapse made bridges safer worldwide. As always, thank you to all my Patreon patrons. You make this channel possible. The Fear Files posts videos covering true stories from history. The channel is made possible by supporters on Patreon and YouTube channel members. Huge thanks to everyone who supports this channel. If you found this documentary informative, please like and subscribe to the channel. Your support makes this content possible. Don't forget to hit the notification bell so you never miss a new video.